In chemistry, reactions don't always go exactly how we want them to go. And oftentimes, our percent yield is a little bit lower than 100%. Now, ideally, we would like to make 100% of the amount of product we would expect due to stoichiometry, but it doesn't always work out that way. So what chemists will do is calculate the percent yield to see how efficient the reaction was. Basically, percent yield is equal to the actual yield divided by the theoretical yield, and then because it's a percent, we multiply by 100. Let's define both of these terms before we try a problem. So actual yield is what the chemist actually gets in lab. In a word problem, you might see words like formed or recovered or made or synthesized. It would be the actual amount of chemical that you're able to collect in a lab scenario. Now, theoretical yield is very different. This is the amount that you're expecting based upon stoichiometry. I'm just going to put stoich for short. And the theoretical yield is usually higher than the actual yield. Now, we would love for our actual yield to be close to the theoretical yield. Sometimes it is, sometimes it's much lower. It really depends on the reaction. Now let's take a look at a math problem based upon percent yield. The question is, what is the percent yield for the following reaction if 1,250 grams of carbon react to form 708 grams of methane? And the hint is find the theoretical yield of methane first. So let's take a look at the two numbers we were given. The first number is 1,250 grams of carbon, and that's a reactant. So I'm going to write that number below carbon in my balanced equation. The other number is that 708 grams of methane form, and that's a clue. That word form means that in the lab setting, this is actually how many grams of methane formed. So that is our actual yield. What we will do is we will save that for the end. We'll use it at the very end in our percent yield equation. So for now, let's just start with our amount of carbon and let's get our theoretical yield of methane using stoichiometry. I'm going to set up a string of equations. First, I convert my grams to moles. Carbon is 12 grams per mole. Make sure my units cross out. Next, look at my mole ratio from the balanced equation. I'm focusing on methane, okay? There's another product. Carbon dioxide is the other product, but this problem really only asked us to focus on methane, so that's what we'll focus on. It looks like the mole ratio is 1 methane forms for every 2 carbons that go in. Moles of carbon, cross out. Our last step would be, excuse me, let me erase it. Last step would be to take those moles of methane and just convert them into grams so that we can compare them to the actual yield. So 1 carbon and 4 hydrogens would be 16 grams per mole. Make sure that my moles of methane cross out. And my theoretical yield of methane is 832 grams. So according to all of this stoichiometry, 832 grams of methane should theoretically form, could potentially form. Now, in order to get our percent yield, we use our formula. which is actual over theoretical, I will abbreviate that, times 100. So I'm just going to simply plug in my actual yield, which is 708 grams, divide that by my theoretical yield, which is 832 grams, multiply that by 100, and see what I get. I am getting 85.1% yield. So an 85% yield, it's not a terrible yield. Ideally, we'd love a 100% yield, but there are many chemical reactions. For example, ammonia. When ammonia is synthesized in a lab setting, the yield is often very low. And so a lot of times, chemists spend quite a bit of time figuring out what temperature and what pressure and what other conditions increase the yield so that they can make their maximum amount of profit. But for this reaction, the yield was 85.1%.